Oh man, we're into types of triangles. 3.6, there ain't just one type of triangle. Well, it's not just that it has three sides. There's different characteristics of different types of triangles. We can classify them not only by their angles, but also by their sides. First one we're going to talk about, isosceles triangle. If two sides of a triangle are congruent and the angles of the opposite sides are congruent, then the triangle is isosceles. Seinfeld, kids, you probably have never seen it. But Kramer said, if I had a child, I'd name him Isosceles. Excellent. And when we're writing this out, we can just write definition isosceles triangle or def iso triangle. Next up, we have our equilateral triangle, which means that we have all three sides congruent. All three sides of the triangle are congruent, then the triangle is equilateral. All right, wonderful. An equiangular triangle, all equal angles, all congruent angles. All right, they're one and the same, though. All right, equilateral, you're going to have equiangular. Equiangular, you're going to have equilateral. Oh my goodness, it's like I could tell the future. There we go. Equiangular, all the angles are congruent, then it's equiangular. But again, equilateral, equiangular, if you have one, you get the other, and vice versa. And lastly, we have our scalene triangle. No pairs of sides are congruent. All three sides are different. It's a scalene triangle. Lovely. In context of a proof, this is kind of like the least useful of the triangles. Like, hey, by the way, none of these sides are congruent. Good luck. Yeah, not really that helpful, but it is a type of triangle. The isosceles triangle is the one you're going to see most. All right, so we have find the measure of each side of an equilateral triangle. What do we know about equilateral triangles? All their sides are congruent. Lovely. All righty, so I could pick really any two or any three, well, any two of these, set them equal to each other and solve, right? Let's do that. 2x plus 2 equals 3x. I'm going to subtract 2x and get 2 equals x. Booyah. I'm done. Oh, I'm not done. It says find the measure of each side. Well, if I plug 2 in, I'm going to have 4 plus 2 equals 6. 3 times 2 equals 6. 10 minus 4 equals 6. All the sides are 6 apiece. Duh. If I do one of them, of course all the other ones are going to be 6. It's equilateral. All the sides are congruent. Whew. All right. We got AD and CD are legs of the isosceles triangle ACD, and B is the midpoint of AC. We want to prove that A and C are indeed congruent. All righty. Well, let's see here. I've got AD and CD are the legs of the isosceles triangle. If it's an isosceles triangle, we know that the legs are congruent. Heck yes. And then I've got that B is the midpoint. Well, if B is the midpoint, then I know it splits into two congruent segments. Woo! Now, how could I prove angles congruent? Well, what if I were to draw this line in and not miss it? That's pretty decent. What do I know about that line? It's congruent to itself. What do I have now? I've got congruent triangles by side, side, side. Is that enough to then show that my angles A and C are congruent by CPCTC? I think so. Let's prove it up. Dang. We made quick work of that one. Made quick work. Okay, let's do this. So I've got let's see here. I've got AD is congruent to DC by the definition iso triangle, congruent legs. Next up, I got AB is congruent to BC. And that would be definition midpoint. Now I want to draw DB. And we could say 2 points determine a line. Or you could say like aux line. That works as well. I choose the 2 points determines a line because that explains what the heck's going on. But really, I don't care. Depending the teacher, they might like 2 points determine a line. Some might like aux line. Either way. Alrighty. DB is congruent to DB. Reflexive property. remember when using an aux line, you want to know something about the line that you're drawing, or the line segment rather that you're drawing. Make sure that you know that it is indeed congruent, okay? Or maybe that it's a radius, and you can link other radii together. All right, know something about the line in which you are drawing. Make it split something into two different triangles. Make sure that line that you draw has a purpose. Okay, enough to prove these triangles congruent? I think so. Triangle A, B, D is congruent to triangle C, B, D by side, side, side. And lastly, but not leastly, angle A is congruent to angle C, CP, CT, C. Woo, woo! Now, there's a worksheet that goes with this one. This is the first problem from said worksheet. All right, we're going to plot some points. All righty. All right, so we want to classify this triangle by sides and by angles. All right, given these 3 points. Sound good? Okay. Well, let's see here. For sides, we're going to need to know our side lengths. Well, I can tell that AC is going to be 12, right? That's a pretty easy one to see. We can just count that bad boy there. That's going to be 12. But I don't know what AB is, and I don't know what BC is. So I'm going to need to find out some lengths, and in order to do that, I'm going to need my distance formula. So if we want a distance, it's going to equal distance equals, you may remember this from Algebra 1, x2 minus x1 squared plus y2 minus y1 squared. Fit it. Nice. And that's all in the square root. Okay? So I'm just going to be using my 2 ordered pairs. Let's set it up for AB, shall we? So for AB, looks like I'm going to probably need to zoom out a little bit. Okay. So for AB, I'm going to have so x2, we'll just work with, sure, we'll do 7 minus 1 squared plus 11 minus 2 squared. In all honesty, the order of the x's doesn't matter. Like I could do 1 minus 7 or 7 minus 1 because once I square it, it's going to become positive, right? So that's 6 squared is 36 plus 9 squared is 81. So that's going to equal, let's see here, the square root of 117. Sounds about right. And let's do the same for BC. So we'll have 13 minus 7 squared plus 2 minus 11 squared. And it looks like I'm going to get, well, square root of 6 squared, that's 36. 2 minus 11, that's negative 9 squared is 81. Oh, look at that. I've got the same thing, 117. Now, normally we try to simplify these radicals. This one can't be simplified, but if it could be, I probably wouldn't do it anyways, because really all I'm looking at here is, are my sides, do I have any congruent sides? Do I have 2 of them? Do I have 3 of them? Do I have none of them are congruent? Well, in this case, since these are both square root of 117 and square root of 117, I've got an isosceles triangle. So iso. And then for the angles, do I have any angles that are bigger than 90? Well, it certainly doesn't appear so, but we probably should do something more so than just the looks, right? So here's what's actually going to happen here. We're going to use, you guys remember the Pythagorean Theorem? Remember that bad boy? I'll do this in blue. Remember a squared, a squared plus b squared equals c squared? Well, that worked for right triangles, okay? Our Pythagorean Corollary, okay, that will allow us to determine if we have a right triangle, if it's an acute triangle, if it's an obtuse triangle. So here's how it works. I'm going to need to move some of this stuff and kind of tuck it away so we have a little bit more room to work. Okay, so this is called the Pythagorean Corollary, as said, and what it looks like is this. if I've got, and I like to rearrange my Pythagorean, I go c squared, I'll leave a little space, a squared plus b squared. Now, if that c squared is equal, then that means that it's a right triangle. If that c squared is less than, meaning if it's smaller than a squared plus b squared, then it's acute. And then if c squared is greater than a squared plus b squared, it's obtuse. Lovely. This is something you definitely want to jot down in your notes, along with, of course, your distance formula. Okay? Those two things you want to have down. So let's classify this thing based on its sides now, shall we? Well, my longest side is always going to be my c. So, well, square root of 117, I have no idea what that is. Wait a second. I know the square root of 121 is 12. So, since it's the square root of 117, it's got to be smaller than that. So my biggest side is the 12. So 12 squared, whoop, is a terrible 2. There we go. 12 squared. And then I'm going to leave like a little box right here because I'm going to fill that in a little bit. And I've got square root of 117 squared plus square root of 117 squared. And this is just another reason why I don't simplify my radicals in these situations, regardless if it could be simplified or not. 117 can't. Regardless, though, when I go to square everything, because the only time I'm using it is 1 to figure out which side is bigger, and I can clearly see that from what I have going on right here. Right? I can get my estimations there. But over here, when I'm squaring it, this is so easy now. Cancels, cancels. And I've got 144, we don't know, and that's 117 plus 117. Well, I'm not even going to finish out adding those together. But is 117 plus 117 bigger? Absolutely. So what is this one? It's that middle option. It's acute. Okay? I know 144 is smaller than that. It's 234, for those of you wondering. But 234 is definitely smaller, or sorry, bigger than 144. So c squared is less than, therefore it's acute. If you didn't get this written down on the last page, pause, write it down, distance formula. You're going to need it. And once again, if you didn't get this written down on the last page, or the, I guess 2 pages ago now, make sure you write it down. So pause it, write it down. You're going to need it. And that's it for today, folks. That is it. Woo! America.